Okay, this video is on notions of convergence. In an inner product space, we can talk about, remember we talked about convergence in a metric space. In an inner product space, we can actually talk about two different types of convergence. Strong convergence, or convergence in norm, and weak convergence, or convergence in inner product. Strong convergence holds for norm spaces. Weak convergence can only be applied, of course, in inner product spaces. All right, so that we say that Xn converges strongly. So actually that should be an S. It converges strongly to X. In other words, Xn converges strongly to X if and only if the norm of Xn minus X converges to 0. And again, remember what this means. It means for every epsilon greater than 0, there exists some n greater than 0 such that the norm of Xn minus X would be less than epsilon for every little n greater than or equal to capital N. So this is what we mean by convergence. Okay, so that's strong convergence. Weak convergence, we say that Xn converges weakly to X, and we write it here with a little w above the convergence. If and only if the inner product of Xn with y converges to X with y for every y in S. So this has to hold not just for one particular y, but it has to hold for every y. And just to note that the example in 2.4 where they show it converges for a particular y is actually a bogus example. Okay, it has to be, this has to hold for every y. But it turns out that there are sequences that converge weakly but don't necessarily converge strongly. Okay, so we have these two different notions of convergence. And associated with that is a theorem. We say that let Xn be a sequence. Actually, I should have written that like that. Xn be a sequence in a norm space X. I'm going to just mark these so I can go back and fix things. I'll fix the notation. Okay, so we have a sequence in a norm space X. Then we do have that if something converges, if X converges strongly, that implies it converges weakly with the exact same limit. But the converse is not true. In other words, weak convergence does not imply strong convergence. So weak does not imply strong convergence. But if the dimension of the inner product space is less than infinity, in other words, if we're in finite dimensional spaces, then it turns out that weak convergence does imply strong convergence. All right, so how do we go about proving such a thing? So if we want to show that strong convergence implies weak convergence, so part A, then we assume strong convergence. Okay, so we know Xn converges to some X star, and that means strongly, which means that the norm of Xn minus X star converges to 0. All right, so now we want to show that it converges weakly. So let y be any element in X. Okay, then we can look at the absolute value of the inner product of Xn minus y minus X star minus y. So if this guy goes to 0, then we have weak convergence. Okay, but that is just by properties of the inner product. We can combine, these two, and we have Xn minus X star with y. And now by the Cauchy-Schwarz inequality, we have that is less than or equal to the norm of Xn minus X star times the norm of y. But we know that this guy converges to 0 because by the definition of strong convergence. So this right hand goes to 0. And of course, the absolute value, this thing is greater than or equal to 0. So since this guy is equal to 0, it's sandwiched, right? We have 0. We have something that's converging down. This guy is sandwiched in here in the middle, and so it has to go to 0 also. Therefore, we have weak convergence. So we've proved part A. If it converges strongly, it converges weakly. Now, before proving part B, maybe let's look at that example 2.4.4 that I talked about in the book. And what it did is it said that, okay, let xn be 0, 0, 0, and this 1 is going to be in the nth element. Now, does this thing converge weakly? Okay, so, and their example was let's let y equal to this particular sequence. Obviously, xn inner product y would go to 0. But does that imply weak convergence? And the answer is no, because it has to hold for every y in X. So we have to have, there may be y's. For example, y is all 1. And this would not converge if it's all 1. Now, if y is in L2, meaning that, which is the set of all, x in L, such that the 2 norm, in other words, the sum of yi squared square root I equals 1 to infinity, has to be less than infinity. Now, if x is in L2, then in fact we can show that the sequence, the tail does actually converge, and we would get weak convergence. Okay, so to prove part B, we need to have a counterexample. So the counterexample would, again, we want to show we want to find something that is weakly convergent, but not strong convergence. So in other words, weak convergence does not imply strong convergence. All right, so we can let xn be 0 to 1, and let x be L2, which is the, so if y is in L2, y, like we said, the 2 norm has to be finite, which means yi has to go to 0. So xn inner product with y is going to be whatever y, it's going to be the nth element of y, and that will go to 0 for every y in x. Yeah, okay. So I guess this converges weakly in L2, but there's no x star, so that the norm of xn minus x star goes to 0. In other words, because this is in the nth element, there's no x star, that it's getting closer and closer. When you take the norm of xn minus x star, no matter what x star let's suppose you said this is convergent to 0, the 0 sequence. If you had all of these elements equal to 0, when you take the norm, you're always going to pull out the difference in the nth element, and so the norm will always be equal to 1 for x star equal to 0. But if x star is anything else, then obviously there's no way for it to go to 0. So this is an example of a case where you have weak convergence but not strong convergence. Okay, so we've shown that in fact for infinite dimensional sets we can get, or infinite dimensional spaces like function spaces and sequence spaces, that weak convergence does not imply strong convergence. So now let's show that for finite dimensions, in fact, we can get that, because in this counterexample, we use the fact that xn is sort of, we had to use this infinite sequence idea so that xn was always pulling out the last, element to get convergence, but convergence weakly, but then, always equal to 1. All right, so this counterexample actually depended on the infinite dimensionality, I guess, of that particular vector space. All right, suppose now that we have a finite dimension space and that xn converges to x weakly, then what we can do is we know that for every y in x, this is true. And now, since it's a finite dimensional space, we're going to go ahead and pick out a basis, an orthonormal basis. So let E1 to EK be your orthonormal basis. In other words, the inner product of EI with EJ is going to be delta IJ. That means that xn can be written in terms of its basis, where each of these coefficients, will be a sequence. And then x star, the thing that it's converging to, can be written in terms of its basis as well. Okay, so because xn inner product with y goes to x inner product with y, when we take the inner product, we get that, in fact, you take the inner product of this guy with EJ, and we get the, it pulls out the jth coefficient. And if you were to take, y with, or x with EJ, then we get AJ. And since this has to be true for every y, we can pick a particular y. So let's pick y equal to EJ. And this means that if you take the inner product with EJ, we get that the coefficients, the jth coefficient. So if we pick 1, this guy converges to that guy. This guy converges to that guy. And you can pick any of, you could pick E1, and you show the first one converges, E2, the second one converges, etc. So you get that every, we basically get that every single one of these coefficients converges to 0. So now if we look at the norm of xn minus x, it's going to be the norm of, xn has this, the nth element, and we can, write that in this way. And now the Cauchy-Schwarz inequality says that I can pull out, each of the coefficients multiplying the basis functions times the norm of the basis function, which will be equal to 1. And we know that each of those guys goes to 0, so the sum of each of these will go to 0. And therefore we get strong convergence. So we've shown that if it converges weakly, meaning it converges in inner product for every single y, then we can construct, we can use the fact that it's finite to ensure that every single term itself goes to 0. Okay, one other idea related to convergence that's important, especially when you're doing analysis and things related to research, is this idea of equivalence of norms. So if the dimension, and again, this is only for finite dimensional spaces, but if the dimension of your inner product space is finite, so it's k, this is finite. I'm going to just highlight that later. And we have two different norms. Like this might be the, this might be the 1 norm and the 2 norm, or the infinity norm, or the 1.3 norm, or whatever. If these are two different norms, then you can find, this means there exists coefficients a and b. These are actually greater than 0. So that the norm of x is bounded above by b times x naught, norm in the the second x in the 0 norm, a x and bounded below by a times the norm of x using the 0 norm. In other words, if I can show that something converges in x0, then it also converges in x, in norm x. So I have these two different norms, say the infinity norm and the 1 norm. If I want to show that it converges in the 1 norm, let's say, but I can construct a proof where it converges in the 2 norm, then that implies it converges into one norm. So in other words, for convergence proofs, it doesn't really matter which norm you use because all of these norms are equivalent to each other. And sometimes that can really help in terms of demonstrating a particular result.